This is AP Calculus BC, and in this video I'm going to talk about section 8.3. And in this section, there's two things really that we're going to focus on: the idea of a slope field, and then also we're going to talk about approximating solutions to differential equations using a method called Euler's Method. So the first thing here is a slope field. And what a slope field is just a way that we can represent all of the possible solutions to a differential equation. So last time I gave you a little bit of a preview of this, and we're going to go into a little bit more detail here. So we talked about the idea of getting a general solution and the idea that you really can't graph all the possible curves that a general solution really represents, because there's an infinite number of curves given by a general solution. So what we do instead is we use what's called a slope field. And what a slope field is just basically a bunch of little line segments that represent slopes at different points. And you can see these two graphs that I've got side by side here are both slope fields. One of them's got a solution curve drawn through it. So the graph on the left, this graph, the way that I create those little segments is I look at my differential equation, and then I just calculate the slope at an individual coordinate. And so, for example, when I'm at the point 1, 0, you can see that on this graph, it looks like I've got a slope of approximately 1. So I'm looking at this slope field line right here. Okay, so that's essentially how that is drawn. Now, usually we're going to use automated systems to create slope fields. We're going to use, there's calculators that will create slope fields. There's computer programs that'll do slope fields for us. But we want to make sure we understand how it works. So we are going to draw a couple of these out by hand. But in reality, if you ever need a slope field, we're typically going to model the general solution through a slope field via a mathematical software application or through a calculator. Okay, so now in addition to a slope field, remember that's the general solution, we can also draw a particular solution through a slope field. So this is the particular solution to my differential equation that goes through the point 0, 1. And if you look at that curve that's drawn through there, you can kind of see how those slope field lines are guiding the shape of that line. When I draw a solution curve through a slope field, I should never cross over one of those slope lines. I should always be between or tangent to any individual slope field line, because those are supposed to represent the slope of the solution curve at any point within the region that's shown in my graph. Okay, so let's talk a little bit about how we create these slope fields. Okay, so I'm going to just draw a couple of these with you, and then I'm going to have you try one of these. So to start with here, let's look at a really easy one. Let's say we had dy dx is equal to x, and we wanted to draw the slope field that would be represented by that. Well, what we do is we just get the slope at any coordinate based on that differential equation. So for example, whatever the x coordinate is here is going to be my slope. So when I'm at, and I'm going to do this in red to make it a little easier to see, when I'm at the point when x is 0, I have a slope of 0. When I'm at the point where x is 1, I have a slope of 1. And so I'm just drawing little line segments that are approximating those slopes. When I'm at x is negative 1, I have a slope of approximately negative 1. So you can see anywhere I'm along the y-axis, I'm going to have a 0 slope. Anywhere along the line x equals 1, I'm going to have a slope of approximately, or I'm going to draw a slope of approximately 1. And then where I'm at negative 1, where x is negative 1, I've got a slope of negative 1. Now that's my slope field. Now that's a really small sampling of a slope field, but it gives me a feel for how these things are created. Now let's take a look at, this is a differential equation we could actually solve. So if we were to separate the variables here, we would have dy is equal to the integral of x dx. And if we solve that out, we would end up with y is equal to x squared over 2 plus c. So that's my general solution. So I'm expecting my slope field to look like a parabola that opens up, and the c value is going to translate that graph anywhere up or down. Well, if we were to choose some point here, and I'm just going to choose the point 0, 0, and I start kind of using my slope field lines to trace through, you can kind of see how I'm creating a graph that looks like a quadratic opening up. Okay, now really to be able to draw a solution curve through a slope field, I need a lot more points than this, but I'm just trying to give you the general idea of how it works. Okay, so let's look at one more of these, and then I'll have you try one of these on your own. So we'll look at one more really easy one. Let's say we had dy dx is equal to y. Okay, so now if I'm going to draw my slope field in here, I'm going to do the same thing I did before, except now my slope is determined by the y coordinate. So anytime I'm at a point where y is 0, I'm going to have a slope of 0. Here y is 1, so we have a slope of 1. And then here y is 2, we have a slope of 2. When you start to get into steeper slopes, it starts to become kind of difficult when you're talking about like a slope of 3 versus a slope of 4 or a slope of 5 versus a slope of 6. You just do your best to kind of approximate what that slope looks like. The main thing is when we draw these out by hand, we're trying to get a general idea of what the slope field would look like. So don't try to make it perfect. Do the best that you can, and keep them as consistent as you can. Okay, so this, just to kind of compare, since we can do it here, if I were to separate the variables this time, I would have dy over y is equal to dx. I could integrate both sides. I would end up with natural log of y is equal to x plus c. And in the end, if I were to solve for y, we saw this back in section 8.2, I would have y is equal to a e to the x power. And you can kind of see, we don't really have enough points, but you can kind of see how I'm starting to look at an exponential shape with this graph if I drew a curve through that slope field. Okay, so now let's move on here and talk a little bit about one that's more difficult. Okay, so I'm going to have you try this one. So here is the differential equation I want you to use. dy dx is equal to 2x plus y. Okay, so now when you calculate the slope at any point, you've got to take the x and the y coordinate into account. Also notice that on this one, if I tried to separate the variables, I actually couldn't solve this differential equation. So a slope field is a really good way for me to represent my solution, since I can't actually get a solution using the methods that we've learned in this class. So take a couple of minutes. I want you to pause the video, get the slopes at those 9 points, sketch them on there, and when you come back, I'll show you the solution. Okay, so here's what you should have ended up with. You will notice that my slope field lines are not necessarily perfect, but it gives me a general sense for what the shape of the solution curve would look like. So for example, when I'm out here at the point 1, 2, that would give me a slope value of 4, because I would do 2 times 1 plus 2. You can see my slope maybe is not a slope of 4, but it's definitely steeper than the slope that I have here. So do the best that you can with those slopes. The main idea is you want to know how these slope fields are created so that when you look at a slope field, you know how to interpret that slope field. In the future, I might make you draw a little bit of a slope field, probably 10 or less points. And so it'll always be something really simple like this. For the most part, what I want you to be able to do is be able to read a slope field and understand what a solution curve would look like from a slope field. Okay, so now going back over here and looking at these slope fields, it makes a little bit more sense, right? Because now we know how this was created and how this solution curve is drawn through there. It's a little bit easier to see. Let's just practice drawing one more solution curve. So let's say we had a solution that had to go through the point, I don't know, this looks like it's around 0, -2. So if you notice here, it kind of looks like I've got a slant asymptote on this graph, and my solution curve looks a little different. So sometimes, depending on the region that I'm in for my graph, I'm going to have different looking solution curves for my general solution. So keep that in mind. But notice when I drew this in here, you can see this point right here. I made sure I didn't cross that slope field line. I'm kind of tangent to that slope field line. So be careful about that when you're drawing solution curves. You want to make sure you're not crossing lines. You're not going to have to draw a lot of these, but I might ask you to draw a solution curve through a slope field once or twice, and just make sure you have the general idea and general sense for how that works. Okay, so let's move on here to talk about Euler's method. So we were just looking at drawing the solution curves through the slope field. So Euler's method is a way that I can more accurately sketch those curves. It's also a way that I can approximate the solution to a differential equation that I can't solve by separating the variables. So what we're going to do here is first talk about how this method works. So you can see that essentially what we're doing here is we're going to say, okay, we're trying to figure out the solution curve, and we're going to approximate it because we can't actually solve our differential equation. So we start at some point that we know. And now we're going to build this solution curve by doing an iterative process using line segments. So we're going to create a line segment going to our next x value by essentially figuring out what the slope of the line would be at the point here based on that tangent slope. We say, okay, let's use a line at that point that uses that slope, and let's go a little bit to the right, and then we'll call that our new endpoint. And then we say, okay, at this new point, based on my differential equation, what's the slope? Okay, once we have that slope, now we do the same thing. Let's create a line using that slope and go some x distance, and now we've got another segment. And you can see as we're piecing these together, you know, I'd have another point that would go pretty far up here. But as I'm piecing this together, you can see how this sort of resembles the solution curve. So the more segments that I make, so the smaller I make that h value, the more accurate my solution curve is going to be. And that's really what we're trying to do, is we're trying to approximate the solution to a differential equation using this method. Okay, so let me go back over here to my blank copy here, and let's talk about how we would do this. So it says use Euler's method to find y of 2 using a step size of 0.5 given that y prime equals x plus y and y at 0 is equal to -2. So when they talk about step size in this problem, that's referring to this h value that you see here. That's essentially how far am I moving in the x direction to get from one point to the next in my linear approximation that I'm making for that function. Okay, so you could go through and you could get the equation of the line and go through a long algebraic process to do this every time. But really what I would prefer that you do is use a streamlined process. And my streamlined process is just going to kind of in a shorthand way represent what we're doing. We're starting at some point. We're going to find the slope at that point. So dy dx that we were given here was x plus y. And then we're going to use the amount that we're going to move in the x direction. That's our step size. Based on that, we're going to figure out how far would we move in the y direction if we went along a line with that slope. And that'll take us to the end of that line segment, x plus delta x, y plus delta y. Okay, so this is kind of a short, easy way that you can do Euler's method. So I'm starting at the point 0, -2. Now, remember, as I go through this table, try to think about what's actually happening here. Okay, we're starting at some point. We need the slope at that point so we can find the equation of the line. Well, the slope at that point, it's just x plus y, so I would get a slope of -2. My delta x, remember, they give us a step size of 0.5. So I'm going to go 0.5 units to the right. If I have a line that has a slope of -2 and I go half a unit to the right, that means I need to go down 1. And at the end of this first segment then, I'm at x plus delta x. I'm now at the point 0.5. And then y plus delta y, I'm going to be at -3. Okay, so that is the end of my first line segment. And now we're just going to keep repeating this process. So now at the end of the first line segment, that's the start of the second line segment. So I'm going to use that same point, evaluate the slope there. It would be -2.5 because we're just doing x plus y. Step size is always going to remain the same every time we're going half a unit to the right. That means we're going to go down 1.25 units. And so this coordinate now, I'm at the point 1, -4.25. Okay, so that's the end of the second line segment. So we've drawn 2 line segments on our graph if you want to kind of visualize what's happening here. All right, so now that's my new starting point, 1, -4.25. If I evaluate the slope there, I'm going to get -3.25. I know I've got a step size of 0.5. If I went half a unit to the right, that means I'm going to go down -1.625. And at the end of this line segment, I'll be at the point 1.5, -5.875. Okay, now remember, that's now 3 line segments we've completed. So the last one, I'm going to start at 1.5, -5.875. I know the slope there is going to be -4.375. Still have the same step size. I'm going half a unit to the right. That's going to make me go down -2.1875 units. And in the end, I'm going to be at the point 2, negative 8.0625. Okay, so essentially what we're doing then is we're approximating the solution to the differential equation at that point. We're saying y at 2 is approximately negative 8.0625. Okay, now in reality, there's some error in my computation, right? Because I'm using a line to approximate a curve. I can decrease the amount of error that I have by making my step size smaller. Now, when we work these out, we're typically just going to do this process by hand so you can get a feel for how it works. The reality is we don't do this by hand. If we did had access to a TI-89 calculator, which we don't really in a virtual setting, I could show you how this is actually programmed into a TI-89, and it's an automated process. But for those of you that know computer programming, you can think how easy it would be to go through this process and just have it, ask you. It could prompt you for the step size, prompt you for the differential equation, prompt you for the initial point, and then, what's your ending point, and then it could go through and it could find it very, very quickly for you. This would be just a simple loop you would set up, and very quickly you can get a solution. So rather than having a step size of 0.5, I could make my step size maybe 0.01 or 0.001. And when you get into some more advanced studies of differential equations, you can start to get into figuring out how much error you're going to have in your solution based on the step size. So there are actually calculations that you can do that will say, okay, let's say I want accuracy in my solution out to the 3rd decimal place. Well, what does my step size need to be? So it's not just kind of a random thing where, okay, I've got some error here. How much error do I have? I can make sure my error is within a certain range by fixing my step size to be a certain size. That's well beyond the scope of this course, but I just wanted you to realize that we're looking at this in a really basic way, and this becomes a really, really powerful tool. So what we're going to do here is just look at one more of these. I'm going to have you try one of these, and I'm going to show you the solution so you can check and make sure you've got this right. And then we'll just talk about a couple of things, and that'll be the end here. So I've got another problem. If you skip that page where it says TI-89 tutorial, we'll come back and talk about that in a minute. So I've got this problem right here that says you're given the same differential equation we just had, x plus y. This time we're using an initial condition for -1. And it says use Euler's method starting with x is 4, 2 steps of equal size to approximate f of 4.2. Show the work that leads to your answer. So I want you to set up that table like I did, and I want you to work through Euler's method. Try to visualize what's happening here. Okay, so pause the video and go ahead and work through that problem. Okay, so here's the solution that you should have ended up with. You can see that I've got the same table set up here, starting at the point 4, -1. You can see my slope, my step size, my change in y, my ending point at the end of that line segment. And then again, I went through the process again, and I'm approximating at 4.2. I'm at about -0.36. Okay, so fairly simple to do. Now, that's really what I need you to know about Euler's method. I'm going to show you this in class, and I'm going to show you on the TI-89 how it's automated and how you can kind of see how this would actually work. There is a lot of information in this notes packet about doing this on the TI-89. So there's this tutorial on the TI-89. There's this information about doing Euler's method on the TI-89. This is not something I need you to know how to do. That's something we do for investigation typically when we're actually in school, and I can give you a TI-89 to work with. So you don't really need to do this. You don't need to understand how to do it on a TI-89, but I left it in here in case you're interested. There are a lot of places where you can go and you can get a TI-89 emulator, and you can work through this process if you're interested. It's just kind of an investigation tool where you can see Euler's method automated and kind of understand the power of this this method as opposed to trying to work it out by hand. Because like I said, by hand, we would never do this by hand. It's just we're trying to understand what's happening when we do this in math software or with a calculator. Okay, so as far as homework goes, you do have homework that's in Wiley Plus. So that's what you should be working on. Now, keep in mind, when I ask you to do Euler's method, this is what I'm going to expect you to do. I don't really want you to write out equations of lines and find the equation of the line and then find the x value and plug in, get the y value. I want you to use this shortcut because this is a much more concise way to write your answer. This is a legitimate way of displaying your knowledge of Euler's method. This is something that is very likely to be on your AP exam. And this is the method I would recommend that you use when you do it on the AP exam, because it's so much more efficient than trying to actually find the equations of the lines and then using those and getting the points off of that. That's going to take you much longer. So this is a streamlined version of that. So just keep that in mind as you work through the homework. Try to practice on the Euler's method questions, actually setting up the table and filling in the table as I've shown you here.